Hello students, welcome to next section, local base for a topological space. So it is also a smallness condition of a topological space in the sense that we are dealing with what will happen to a neighborhood in a topological space, a neighborhood of a point in a topological space. Okay, let's define that basic definition. Let X be a space, that means X2 be a topological space, X2 be a topological space, comma, and X is a point in capital X. If X is a point, small x belongs to capital X. Okay. A local base at X. We are defining a local base at X, which is a collection. It is a collection denoted by L, script L, collection L of neighborhoods of X such that if N is a neighborhood of X, then there exists an L belongs to script L such that X belongs to L and that L is contained in N. So suppose we have a topological space X2. Okay, we take a point small x belongs to capital X. Now we will define a local base at a point X. Corresponding to every point we can define different local bases. Ready? So a local base is nothing but a collection, script L. It consists of neighborhoods of X. L is nothing but neighborhoods of X, or set of all L such that L is a neighborhood of X. Okay. Now this collection is called a local base at X if we consider any arbitrary neighborhood N of X, then there is an element L in script L such that X belongs to script L and that script L is contained in N. Okay, that means in between the point and any neighborhood N, there is a element from script L. So that L can be called a local base at X. Ready? This is the definition of local base. Now, a topological space X2 is said to be first countable at X. Another definition. This is another definition. First countable at X. A topological space is said to be first countable at any point X if there exists a countable local base at X. So a topological is said to be first countable. First countability is defined at a point X if there exists a countable local base at the point X. Okay, and definition of local base is defined in picture. And the space itself is said to be first countable. X is said to be first countable. If it is first countable at each of its points. So there are three definitions. First one is local base. Second one, whenever a space at a point X have a countable local base, that means the corresponding collection is countable, then we say that space is first countable at that point. If it is first countable at all of its points, then it will be the space itself is first countable, or the space X satisfies first countability axiom. Okay. So the easiest example for a first countable space is metric spaces. So for example, let XD be a metric space. XD be a metric space, arbitrary metric space. We take a point which is a non-empty set, X belongs to capital X. Okay. Now I am going to define a collection script L which is equal to set of all elements of the form BD of XR such that R greater than 0. What is this? Corresponding to this point, we take some radius R greater than 0, that may be any positive number, and you consider an open ball centered at X with the radius R in the corresponding metric space XD, where D denotes the corresponding metric. So it is nothing but we have it metric space XD. Okay, we take a point X belongs to XD. Then you consider you can take any radius R greater than 0. If I choose R equal to 1, it is an open ball of radius with a unit radius. And if R equal to 2, it is an open ball with the radius 2. The center point is fixed. We are varying corresponding radius of that open ball. This will be clearly a collection of nothing but open balls centered at the point X. Okay, I am going to prove that this script will form a local base for the space XD. For the space XD. Okay. So for that, we need to verify the definition. What is the definition? L is a collection which is called a first local base. If N is any neighborhood of X, then there is a required property. Okay, so I choose a neighborhood. Let N be any neighborhood of X. So you can consider X the metric space as a topological space too. So by the definition of neighborhood in topological space, if N is a neighborhood of a topological space, a neighborhood of a point in a topological space, then by definition of neighborhood in topological space, there exists an open set U of capital X such that X belongs to U and that U is contained in N, which will be the definition of neighborhood in topological space, which implies U is an open set containing the point X, which implies X is an interior point of U. So by the definition of interior point in metric space or as well as in topological space, in metric space I can say that since it is an interior point, there is a neighborhood which is fully contained in U. So in order to define a neighborhood in metric space, we need a radius. That means there exists some R greater than 0 such that the neighborhood is denoted by actually BD of XR. BD of XR on open ball centered at X with some radius R greater than 0, which is fully contained in U, and we have this U is contained in N, right? So which implies what you get now, if N is a neighborhood of X, then there exists some R greater than 0 such that BD of XR is contained in N. Okay, and X is also belongs to this one because it is a neighborhood. Okay, so what is BD of XR? BD of XR, since R is a positive real number, BD of XR is nothing but is an element in script L, because script L consists of such type of elements BD of XR. So which implies you take BD of XR is equal to some L. I let BD of XR is denoted as some L1, then then I can write for every x in capital X comma, what I can write, there exists an L1 in scriptural such that for x in capital X there exists some L1 in scriptural such that x belongs to that L1 and that L1 is contained in N where N is a neighborhood of X, which implies scriptural is a local base at X in the metric space XD. So XD have a local base of the form collection of open balls or neighborhoods. Okay. Now I consider one more example. Instead of this scriptural, I denote one more set. Some scriptural is equal to collection of all BD of XR, comma R greater than 0 and R belongs to Q. Rationals. So we are considering and the neighborhoods in a metric space with rational radius. Since R is varying over Q is countable. This collection എത്ര R ഉണ്ടോ അത്രയുമാണ് ഈ ആറിനനുസരിച്ചിട്ടാണ് ഈ സെറ്റ് വേരി ചെയ്യുന്നത്. Ready? Since R is varying over Q and Q is countable, this collection is countable. Since Q is countable, so I take this is some L dash, okay. Script L dash is countable. And since BD of XR, R greater than 0 form a local base, this collection will also form a local base. Okay. Because Q is dense in R. And L dash is a local base for at any point in the metric space XD. So every metric space has a countable local base. It is of the form BD of XR, R greater than 0, R belongs to Q. So this collection of L dash, this kind of L dash will form a countable local base at any point in metric space. So we can say that every metric space is first countable, which implies every metric space XD is first countable. So which is an example for first countable space 2. And for another example, I consider real line with the usual topology. I denote tau u as usual topology, standard topology. Okay. Now I define script L is equal to set of all x minus 1 by n, comma x plus 1 by n. Interval of the form x minus 1 by n, comma x plus 1 by n, where n is varying over n, and this where x is a point in capital X. For any x in x, comma, I take L is equal to interval of the form open interval x minus 1 by n, comma x plus 1 by n is varying over n. And you can easily be seen that since n belongs to n, natural numbers are countable. Therefore, L is clearly countable, which implies script L is countable. Now I am going to prove this L is a local base for R. I claim that this L is a local base for R with the usual topology, real line with the usual topology. So how will you prove it is a local base? You consider any neighborhood. Let X is a point in R. Okay, we take a point and N be a neighborhood of X. Okay. Since n is a neighborhood of X, it is of the form by definition, which implies there exists an open set U such that X belongs to U and that U is contained in by the definition of neighborhood in topological space. Since U is an open set containing the point X, it is of the form So here I will take u is of the form a some x minus r x plus r, where r is a positive real number, r greater than 0 belongs to real number. Because it is a usual topology, the open intervals are, the neighborhoods or open sets are of the form open intervals, and it is of the form some x minus r x plus r. Okay, by the definition of usual topology, u will be of the form some x minus r x plus r. Okay, since r is a real number, positive real number, you can use the Archimedean principle by Archimedean property. There exists a natural number n such that 1 by n is less than r. By using Archimedean property, I can write 1 by n will be less than r. Okay, so 1 by n is less than r means what will happen to this interval? X minus 1 by n, x plus 1 by n will be contained in x minus r, x plus r. Because r 1 by n is less than r is greater than 1 by n. So which implies, and what is this? Which type of elements are belongs to scriptural, right? So this can be taken as some L. So I take this equal to some L. Then what do you get now? If x belongs to R and n is a neighborhood of x, then there exists some L in scriptural. That L is of the form x minus 1 by n, 1 by n. This n is given by we are getting n by using Archimedean property, such that x belongs to L and that L is contained in n. How that L is contained in? This L is actually contained in this stage, and x minus r, x plus r is contained in, this is actually u, and this u is contained in n. So which is nothing but u, and this u is contained in n. So together implies L is contained in n. So you get x belongs to for every x in R and n is any neighborhood of x, then there exists L in L such that x belongs to L and L is contained in n, which implies script L is a local base at x which is also countable. So which implies L is a countable local base at any point x, which implies our topological space real line with the usual topology is first countable because at any point we can define local base L of the form this, then it will form a local base at any point. For any varying x, we get different local bases for different points, and this collection is also countable. So we get a countable local base. Therefore, real line with the usual topology is first countable. Okay. Now we will see what is the relation between first axiom of countability and second axiom of countability. First axiom means first countability. Second axiom of countability means second countability. So first countability and second countability are two properties of a topological space. Second countable means it has a countable base. First countable means it has a countable local base. So these two are actually different in nature. And now the relation between them is every second countable space is first countable. Every second countable space is first countable. Very important. First countable. Second countability always implies first countability. So how will you prove this? So let X2 be a second countable space. Second countable space. Then by definition it has a countable base, which implies tau has a countable base B. Countable base script B. Now I want to prove that our space X is first countable, means first countable at each of points. We have to prove that capital X is first countable. That means it is first countable at any point. So arbitrary point. So I will prove, let X belongs to capital X be taken arbitrary point, and we prove capital X is first countable at X. Since X is arbitrary, it will be first countable at each of its points, therefore it will be first countable. Okay. So how will we prove our space capital X is first countable at X? For that, we want to define a countable local base for capital X. So now I will define script L is equal to a collection which is nothing but set of all B in script B such that X belongs to B. So corresponding to any point X in B, X in X, we can consider a base element, right? Since X2 is a topological space, if you take any point small x in capital X2, you can consider a point, that means you can consider a element B in our base script B, right? So ഏത് പോയിന്റ് എടുത്തു കഴിഞ്ഞാൽ ആ പോയിന്റ് ഏതെങ്കിലും ഒരു ബേസ് എലമെൻറ്റിലായിരിക്കും ബിക്കോസ് എവറി എലമെൻറ്റ്സ് മസ്റ്റ് ബി ബിലോങ്സ് ടു എനി ഓഫ് സം ഓപ്പൺ സെറ്റ്സ് റൈറ്റ്, open or closed sets, right? Since and you know every open sets can be considered as union of elements of base elements. So for any element X, that may be belongs to any one of some base element. Therefore when this X belongs to some B, that B is taken in this collection. അപ്പോൾ ഈ എക്സ് സ്ക്രിപ്റ്റ് ബിയിലുള്ള ഏതെല്ലാം എലമെൻറ്റ്സിൽ ഇൻക്ലൂഡ് ചെയ്യുന്നുണ്ട് ദാറ്റ് മേ ബി ഫൗണ്ട് ഇൻ more than one elements in script B. അപ്പോൾ ഈ എക്സ് മേ ബി B1 ഉണ്ടാവാം, B2 ഉണ്ടാവാം, B3 ഉണ്ടാവാം, എക്സെട്ര. ഓക്കെ, അപ്പോൾ ഈ എക്സ് കോമൺ ആയിട്ട് വരുന്ന എല്ലാ ബേസ് എലമെൻറ്റ്സും ഞാൻ ഇവിടെ എടുത്തിട്ടുണ്ട്. സോ ഐ കൺസിഡർ സെറ്റ് ഓഫ് ഓൾ ബേസ് എലമെൻറ്റ്സ് ഹാവിങ് എക്സ് ആസ് കോമൺ. ഓക്കെ, നൗ ഐ എം ഗോയിങ് ടു പ്രൂവ് ദാറ്റ് ദിസ് L is a countable local base. Okay. Clearly script L is countable. Why? Countable because elements are varying over script B and script B is a countable collection, right? Countable since script B is countable. Since script B is countable, elements in local script L is varying on script B, therefore it will be countable. Now we need only prove that it is a local base at X. So we claim that script L is a local base at X. So for that I choose a neighborhood. Let N be a neighborhood of X. Then by definition there exists an open set U of X such that X belongs to U and that U is contained in N. By definition. Okay, since U is an open set, U will be belongs to tau. Right, and U will be belongs to tau and B is a base for tau. So when you get an open set and B is a base for tau implies by the characterization of base I can write there exists a B in script B such that X belongs to B and that B is contained in U, which is a characterization of base by characterization of base. When you get a point which says that the characterization of base says that suppose X to be a topological space, B is a base for tau, then if you have a point X and an open set U containing that, then there is a base element B in script B such that X belongs to B, that B is contained in U. ഇവർക്ക് രണ്ടുപേർക്കും ഇടയിൽ ഒരു ബേസ് എലമെൻറ്റ് ഉണ്ട് എന്നാണ് ക്യാരക്ടറൈസേഷൻ പറയുന്നത്. സോ ബൈ ദറ്റ് ക്യാരക്ടറൈസേഷൻ ദർ വിൽ എക്സിസ്റ്റ് ബി ഇൻ സ്ക്രിപ്റ്റ് ബി സച്ച് ദാറ്റ് എക്സ് ബിലോങ്സ് ടു ബി ആൻഡ് ദാറ്റ് ബി ഈസ് കണ്ടെയ്ൻഡ് ഇൻ യു. സോ വിച്ച് ഇംപ്ലൈസ് when X there is a B in B such that X belongs to B, B is contained in U means X belongs to B is here, right? Whenever X belongs to B, that B will be belongs to this collection L, right? So this B can be considered as some L because the collection of B's containing X will be belongs to L implies E B എവിടെ ഉണ്ടാവും, L ഉണ്ടാവും അല്ലേ, which implies I can write X belongs to L is equal to this B. Okay, I choose some B naught. There exists some B naught in script B such that X belongs to B naught and B naught is contained in U. Okay, so x belongs to L, L is taken as some B naught, then x belongs to L and that L is contained in U. What is U? U is contained in N. So L is contained in U, U is contained in N. So what you get now, if you take any neighborhood N of x, there exists some L in script L such that x belongs to L and that is L is contained in N. It will be true. Which implies script L is a countable, actually it is a local base and which is also countable. So it is a local base at x. Since it is countable also, this L is a countable local base for x. Since x is arbitrary, capital X has countable local base at any of these points, any of its points. Therefore, capital X is first countable. So we proved that capital X is first countable. Therefore, second countability always implies first countability. So the theorem says second countability always implies first countability. What about the converse part? First countability implies second countability will not be true. That means converse of the theorem need not be true. Because you can consider some example. You consider a real line with the semi-open interval topology, tau ls or tau rs, left semi-open and right semi-open, real line with any of these. Okay, tau rs, semi-open interval, real line with any semi-open interval topology, So which is not second countable. We already proved that this collection or this topological space is not second countable. It is not second countable. But I can prove that it is first countable, but it is first countable. So to prove it is first countable, we need a countable local base. You take L is equal to set of all intervals of the form, neighborhoods of the form x comma x plus 1 by n closed, not closed, open, x comma x plus 1 by n weighting over script n. And you can prove that this is a countable local base for real line with the semi-open interval topology. Therefore, it is first countable. But it is first countable if L is equal to L, then L is a countable local base for real line with the semi-open interval topology. So which is first countable but not second countable. Therefore, I can ensure that first countability doesn't imply second countability. Okay.